Okay, think back to 1995. The Hubble Space Telescope did something, well, truly bold.
Uh,
It stared into what looked like a completely empty patch of sky.
right. I mean, pointing that kind of instrument, that powerful, precious tech, at nothing.
Exactly. Seems crazy, but what it found back then was absolutely breathtaking.
It really was.
Suddenly this void, it was just filled with thousands upon thousands of galaxies.
Yes, some stretching back over 12 billion light years.
The Hubble Deep Field, it stunned everyone, showed us that these supposedly dark, empty bits of the universe were actually teeming with light.
Ancient light.
Ancient light from ancient galaxies. It was such a profound glimpse, into the real depths of time and space.
Absolutely.
Okay, let's unpack this.
Yeah, and what's fascinating here is how, like, 3 decades later, we have a new telescope that's pushing that boundary even further,
Right.
kind of radically reshaping what we even thought we knew about the universe.
So this is the European Space Agency's Euclid telescope we're talking about.
That's the one. And get this, in just 1 week of observation,
1 week.
1 week, this incredible machine imaged over 26 million galaxies.
Wow. 26 million.
And some of those are more than 10 billion years old. The clarity, too. The clarity of Euclid's deep field images is just, well, it's remarkable.
What kind of things are we seeing with that clarity?
Seeing these perfect Einstein rings.
Ah, the cosmic mirages, where gravity bends light.
Exactly. Those beautiful rings formed by light from a distant galaxy getting warped, plus intricate galaxy clusters. And you can even start to see the faint sort of thread-like structures.
The cosmic web.
Yeah, the cosmic web itself, these
Yeah.
filaments connecting everything. Euclid's mission is incredibly ambitious. It's not just about mapping the stuff we see.
Okay.
It's about mapping the hidden structure,
Yeah.
trying to really uncover the mysteries of dark matter and dark energy.
Right, the big unknowns.
Totally. So you can say where Hubble showed us the sheer beauty and like the scale of the distant universe, Euclid is now revealing the invisible forces that actually shape it all.
Because the visible stuff is just a tiny fraction, right?
Exactly. Everything we can see, stars, planets, galaxies, everything familiar that makes up only about 5% of the observable universe, just 5%.
That's wild.
It is. The rest is hidden. It's composed of these two really mysterious components. Dark matter.
Which we only know is there because of its gravity.
Precisely. We detect its gravitational pull on the visible stuff. And then there's dark energy, which is, frankly, even more enigmatic.
The force pushing the universe apart faster and faster.
That's the one. Accelerating the expansion. So what Euclid really forces us to confront is that our whole way of seeing the universe, it only covers this tiny fraction of what's actually there.
It's like we've only been looking at the foam on top of the ocean.
That's a great way to put it. It's not just about building a bigger map. Euclid is building a map that actually redefines the territory itself. What is?
That's a mind-bending thought, isn't it? That everything we've ever observed, everything we thought was the universe, is just 5% of reality.
It really is.
And Euclid is literally pulling back the curtain on the other 95%. But,
Yeah.
okay, how challenging is that? I mean, how do you see something like the cosmic web, or especially dark matter, if it's fundamentally invisible?
Yeah, that's an excellent question. And that challenge is exactly what makes Euclid so revolutionary.
Okay.
We can't directly see dark matter or dark energy. There's no, picture of it. Instead, Euclid observes their influence, their effects.
Right.
So for dark matter, it very, very precisely measures how the light from distant galaxies gets distorted.
The lensing thing again.
Exactly, the gravitational lensing. The gravity of these unseen clumps of dark matter bends the light passing by. Those Einstein rings, they become incredibly valuable data points, not just pretty pictures.
Ah, okay, so you map the distortions to map the dark matter.
You got it. And for dark energy, it's different. Euclid meticulously measures the expansion rate of the universe over cosmic time.
How? By looking at galaxies.
By looking at billions of galaxies at different distances and therefore different points in cosmic history, it tracks how the expansion has changed.
Wow. So the biggest hurdle must be the precision needed.
Absolutely. The sheer, almost unbelievable precision required. We're talking about detecting tiny, incredibly subtle distortions and changes across billions of light
It
years.
sounds almost impossible.
It's like, imagine trying to map an entire hidden city, completely invisible, just by observing the subtle ripples its presence creates in a vast, distant ocean. That's kind of the scale of the task.
That analogy really helps put it into perspective. The scale is just enormous. So if we connect this to the bigger picture.
If we connect this to the bigger picture, Well, Euclid isn't just about collecting, tons of data points. It's fundamentally about trying to answer some of the most profound questions humanity has ever asked.
Right.
Like, what is the universe truly made of? Beyond the 5% we knew about. How did it all begin? And crucially, what will its ultimate future look like? Is it going to expand forever? Will it collapse? Something else.
Big question.
The biggest. By meticulously mapping how galaxies and dark matter are distributed and measuring that expansion history really accurately,
Mm-hmm.
Euclid is giving us the tools to actually test our current cosmological models to see if they hold up or if we need, well, new physics.
Wow. So it could rewrite the textbooks?
Potentially, yes.
Yeah.
And this mission is going to leave behind this incredible legacy data set. It won't just map the cosmos in unprecedented detail right now.
Right.
It'll serve as a foundational resource for really decades of future discoveries. Astronomers will be digging into this data for a long, long time. It's set to operate through at least 2029.
So the discoveries will keep coming.
For years, yeah.
Okay.
It's truly a testament to scientific ambition, I think.
It really is, isn't it? And just think about this again. You mentioned it earlier in its first week. Euclid covered only, 0.4% of its planned survey area. Less than 0.5%.
That's right. Tiny fraction.
And it still managed to detect over 26 million galaxies.
It's staggering.
And the overall mission aims to observe more than 1.5 billion galaxies in total.
1.5 billion, yeah.
So what does this all mean? It means we're only seeing the very, very tip of the cosmic iceberg right now with Euclid.
Absolutely. The potential is enormous.
What more will this incredible mission uncover as it keeps going, as it continues its quest to map that invisible scaffold of the universe? It's almost impossible to really comprehend the scale of discovery that might be waiting for us.
It really makes you wonder.
It does. Speaking of incredible maps, if you're curious about how we're charting our own cosmic backyard, the Milky Way.
Ah, Gaia.
Exactly. You might be interested in our deep dive on the Gaia Observatory. It recently revealed the most accurate map of our galaxy ever made.
An incredible achievement in itself.
Totally. Based on 3 trillion observations of over 2 billion objects across 11 years. Just nuts. So if you missed that deep dive, definitely make sure to catch up on that exciting milestone in galactic cartography. It ties in nicely with this theme of mapping the cosmos, both near and unimaginably far.